CS 402 on Monday, June 23rd, 2014.
All right, let's get started. Kernel 1 is due a little less than 2 weeks, so, the idea is that it's the summer, you're only taking one class, you should spend all your time doing this project. Kernel 1 and 2 is not so bad, but, you should start early. Okay, read the kernel FAQ, start using GDB right away. If you are having trouble, please come to office hour. I have trouble with, I think people are complaining. Some people say GDB doesn't work or things like that. Come to office hour to me or the TA's office hour. Okay? And again, if you have code from previous semester, be very careful not to copy from it. Best to get rid of it. Please only run Unix on Ubuntu 12.04. If you run into anything else, you might run into trouble. Don't waste time running in any other system. Okay? The kernel team formation period is over. There are basically two students who do not belong to a team. One student is listed over here, and the other person, I haven't got an okay from him to release this information. So if you would like to include the student in your team, even if you already have 4 students, I would allow it. So this is the only way you can have more than 4 students in your team. Okay, so send her an email. Talk to her and see if this is what you like, and I guess in the end she can decide, which team she wants to join. All right, but this needs to be done like right now because kernel 1 is going pretty fast. Some of the stuff that I just want to mention to keep you out of trouble in the kernel assignment: your team needs to meet often. Once a day is preferred. And you should work at the same place at the same time. That will be the best place. Find a place, hang out there for 3 hours a day or something like that. Have lots and lots of discussion and write a fair amount of code. Okay, so talking about it to understand what's going on. That's the most important thing. Okay, use the lectures to sort of guide you of what you need to do. A little note over here: swallow your pride. Be honest with your teammates. Don't hide your weakness. Don't make promises that you cannot keep. Okay. Everyone gets the same grade, so you're working together as a team now. Okay. You can tell people that, hey, I'm not really good at programming or whatever. And then if everybody's saying the same thing, what do? Well, somebody has to step up. Okay. Somebody says, hey, I really want to learn this thing. I want to spend all my time this summer on this thing. Okay, and I'm just going to dig in my fingers and I wouldn't let go until I get everything to work. Okay, so that's the right attitude to learn this thing. Okay, but in the end, it's going to be very rewarding because you're going to learn something you don't think that you can possibly learn. Okay, so that's a really good feeling. All right, and the other thing is that you don't have to know what every piece of code is doing. Okay, it's a large piece of software, but it's the operating system, right? It's huge. Okay, there's no way for you to learn everything, so you need to sort of, you sort of need to learn how to assume that everything else works. Okay, that might not be what you're used to, but that's sort of your only chance is to assume that other stuff are working. Okay, so to figure out how to, what do you assume about other stuff? Well, it's kind of like the lectures. Okay, so you assume that other things are working like the lectures. Okay, and focus on what you need to do. Okay, you need to do grep. okay, a lot to get an idea how a function is being used and how, a field in a data structure is used. Okay, just to grab all over the place, try to find where it's being used, and try to guess, what this thing is doing. All right, and then talk amongst each other, post to the class Google group, talk to me. I mean, I should be your main, also your main resource for getting help, or your classmate, which has a probably much faster turnaround time than me, but I'm really here to help you. Okay, so send email to me. Don't be afraid. All right. Okay, so we have a lot to cover, and my plan is today is to cover section 5.0 and maybe at the beginning of 5.1, and that should give you everything that you need for kernel 1. Okay, so hopefully by the end of today's lecture, you should have everything you need. There's one thing. So I had an extra lecture last Wednesday afternoon. I hope that you have seen it. I just want to sort of finish it up on a couple of useful points. In booting. Okay, so last time we talked about, the power up, what is this? Power up self-test. It counts the amount of memory and it passes it to the operating system. So all these things are sort of at the lower level. You can say that while they're at the hardware abstraction level, right? Eventually, they get the kernel to run. Okay, and we talk about, booting, and how do you start from, the CMOS, a booter that are sitting on, well, the BIOS booter that's sitting on the CPU board, and that reads, data in, and then start, booting, from that point on, right? So over here, I guess the last thing that we were at is this slide, okay, talking about, on the Windows, system. One of the last things that it did right before, trying to get, sort of into the kernel. Is to find the next, tiny operating system to boot. Okay, and this is where the next tiny operating system is for Windows system. That's it's called the master boot record from the first hard drive. Okay, in the good old days it was the floppy drive, but these days it's a hard drive, and it's going to go to cylinder 0, head 0, sector. I have a typo over here. It's sector 1 on the hard drive. Okay, and the first disk is going to look something like this. Okay, so this is the one sector of the drive, and this one is actually very small. It's 512 bytes. Okay, so there are 2 bytes down here called the magic number. It sort of tells you that this this particular hard drive is formatted for this particular use. So magic number usually is something that's hard coded, and they just call it magic number. Okay, and then the next 64 bytes are the partition table, right? If you use a Windows machine, you should be familiar with the partition table. It has 4 partitions. Some of them could be a logical partition to have a, you can create a bunch of drives into a logical partition. Okay, and then sits the boot program. Okay, so the boot program is tiny, right? You can see that, in the good old days, 512 bytes, so that's at most 446 bytes for the boot program. And these days, the sector is a little bigger, so the boot program might be a little bigger. Okay. All right, so for MS-DOS, they have some kind of boot program, but these days, we're talking about Unix, right? So for Unix, the boot program, there are 2. One is called Lilo, and that's kind of old. These days, they're using Grub as the boot program. Grub is pretty advanced. They actually knows about file system structures. So they actually understand Unix file system. You can actually tell Grub, say, I want to boot from a certain file, on that particular hard drive. Okay, and the file can even be compressed. So that's what the system are using these days. Okay, so this one, what it will do is that it will try to bring in, the next kernel, and also try to sort of configure the kernel. Okay, so the step for Linux sort of looks like that. Looks like the following. Okay, so there are 3 different steps in the beginning, right? Once you know the location of the kernel is brought into memory and is compressed. So usually the kernel image is compressed, okay, and it will uncompress it and put it into memory. Okay, set up things like the stack, BSS, all these kind of stuff for the kernel, and all these things are done in assembly code. So you can think about, sort of there in the hardware abstraction layer. Okay. Then it creates something called the process 0. Okay, So it will initialize the page table, get ready, to run, real processes, but still you're just running the kernel. Okay, so it will turn on address translation. Okay, so what happens is that in the processor, there's actually two modes. One is that when the processor is running, they will talk directly to to the hardware memory without any address translation, without using any virtual memory. Okay, so you will see that during this point in the Linux booting process, this is where address translation is turned on. So from this point on, it's using virtual addresses. Okay, so from this point on, we're basically in chapter 7, talking about doing everything in virtual memory. And last lecture, we also talked about how virtual memory is used. Okay, so pretty much all the kernel are running beyond this point is using virtual memory. Okay, so even the operating system is using virtual memory. So not only users are using virtual memory, so is operating system. So that's kind of weird. So as we go into chapter 7, it's going to become more clear how this is all working. Okay, and also when you start working in kernel 3, it's going to make clear. Okay, so it's kind of weird that operating system is also running using virtual memory. Okay, so it's going to set up page tables in virtual memory space. Okay, so there's some kind of a circular reasoning over there, but as it turns out, it will actually work. All right, so at this point, process 0 knows how to handle some aspect of paging, and then it goes into the next level. It transfers control into the kernel, and this one is written in C code. Okay, so you go beyond the hardware abstraction layer and go into the actual kernel. Okay, so at this point, you initialize the rest of the kernel, create the init process, and this is process number 1. Okay, and this function, those of you who have started looking at the Unix code, right? This function is bootstrap. Okay, so that's the first place. There's the code says not yet implemented, and that's where you have to implement. Okay, so your kernel assignment 1 basically starts right here. Okay, so keep in mind that your kernel is really, Unix is really not Linux. So this is the Linux booting. So it doesn't really completely look like that. If people have to know, how do we get here and stuff like that, try to figure out all the other code, it's going to take a long time. I suggest you don't spend too much time doing that. Okay, and just assume that all these other stuff are working properly and you're brought into Bootstrap. And this is where you need to create the most important process, which is called the init process, which is going to start everything off. All right? Okay, so once you get into, the C-based kernel, well, then you can just write all your C programs, and you can see from the Unix kernel, you can start from scratch to implement everything. All right, create the init process create other processes, and then, you have a process tree, and then you go from there. All right? So a little bit about device driver. In the good old days, right, you start with the device driver on the motherboard, and then as you load into the operating system is going to come with additional device drivers. So, the device driver on the motherboard seems to be very limited because you only get to upgrade it once in a while when you get a brand new system, or you actually can upgrade your device driver. You can upgrade your BIOS if you go to the manufacturer's website to upgrade it. So that's really not that flexible. These days, beyond BIOS, what people are using more is that they're using bytecode. Okay, they are having their basically bootloader written in high-level language get compiled into bytecode, and on the lower level, at the BIOS level, they will have this bytecode interpreter to support that. Okay, so Microsoft is doing that, Sun is doing that, and also Mac is also doing that. So that seems to be the current way of doing booting. All right, so that's all I want to say about booting, and now we're going to go into chapter 5. All right, so chapter 5 is one of the main chapter in the textbook, right? We're gonna go to chapter 5, 6, and 7 cover processes and threads, file systems, and virtual memory. Okay, so we're gonna see how threads and processes, these kind of stuff, well, how threads are implemented, right? Because the threads are an abstraction of the CPU, and processes are an abstraction of memory. So we're gonna leave that to chapter 7. All right. Okay, so we're going to talk about things like, threads implementation, how to implement mutex on uniprocessor and on multiprocessor, and also talk about interrupts, right? So this is, I think this is like section 5.1 or 2, I can't remember. And the beginning part is what we need to cover so that you can, so you know everything that you need to know for kernel 1. All right, so we're going to look at how threads are implemented. In the beginning, the first thing we're going to cover is some kind of a strategy of how different approaches there are for implementing threads, okay? And then we're going to sort of put that aside and talk about the actual, how do you implement threads, okay? And also, what does it mean to implement a thread, right? Thread is something that runs in the CPU. How do you implement that? You just give it a CPU and it runs, right? Okay, so the question, of course, is how do you switch from one thread to another, and things like that. All right, to support multiple threads or support the abstraction that all these threads are using the CPU without, seeing each other. Or if they want to see each other, how do they cooperate with each other? All right? Okay, and then we're going to see how to do that on a multiprocessor. All right, the different kind of strategy for implementing threads, okay, the number one question that you have to ask is, where are threads implemented? Are they implemented in the kernel, or are they implemented in user space? Okay, so it turns out that both options are possible. They have their own strengths and weaknesses, so, different systems might decide to go in a different approach. Okay, so they're all viable solutions. So we're going to talk about a few different things. One is called the one-level model, okay, or like the one-by-one model. Okay, and then we're going to talk about the two-level model, and there are different names for it, like n by 1, n by n, something also called scheduler activation model. These three different approaches are, kind of different. Okay, so we're going to sort of briefly talk about, what they are. Okay, we're going to start with the simplest thing is one by one. Okay, so the one by one, the picture over here is very simple. You have many processors on your system. Okay, and then every user thread is supported by a corresponding kernel thread. Okay, so this is pretty much the premise that we sort of have talked about in the previous semester, previous lectures, right? That if you're running a thread in the user space and then you make a system call, you trap in the operating system, there's another thread there to support it. Okay, so if you have 20 user threads, well, you have, and all of them can make system calls, so you got to have 20, kernel threads. Okay, so every user's thread is supported by a kernel thread. All right, so what is the implication over here? Right, the implication over here is that, the threads are implemented inside the kernel. Okay, so, so that's why you are aware that every user thread is out there. Well, because you have, in the kernel, you have created a thread to support it. Okay, so therefore, all the important stuff happening about the threads are inside the kernel. Okay, so therefore, if you call things like pthread create in the user library, right, pthread create, the pthreads library is just a standard. Okay, the way you can implement it, you can implement that standard without the support of the operating system, everything done in the user space, or with the support of the operating system. Okay, in the one-by-one model, or the one-level model, you're supporting that in the operating system. Okay, so therefore, when you call pthread create, the threads are implemented in the kernel, well, that's a system call. Right, so every pthread create is going to turn into a system call. You go into the operating system is going to create a thread, control block, right, to represent that thread, and also it's going to create a kernel thread inside the kernel, and that guy's going to have a stack, and then in the user space is also going to have a stack, right? So the picture sort of look like this, right? Here's user space, here's a kernel space, okay? If you start with a process inside over here, you run a thread. So down in the kernel, there's going to be a kernel thread corresponding to it, and there's going to be a kernel stack associated with that thread, right? Because remember, when you make a system call, you got to use the kernel thread. The kernel thread has a kernel stack because we don't trust the user stack. Okay, so inside this address space, there's going to be a user stack, and inside the kernel space, there's also going to be a kernel stack. Okay, and now what happens when you call pthread create, right? You create another thread over here, which means that you need another stack in the user space. You need to create another stack in the kernel, and you need to have another stack in the kernel. All right, so in this case, you have to make a system call into the kernel to implement pthread create. All right, is that bad? I mean, think about your warm-up number 2. How many times do you call pthread create? 3 times, right? 4 times, so whatever, right? Okay, so if you do this, even though it's a system calls are slow, right? It takes, I don't know, the tens of thousands of machine instructions, or maybe several thousand machine instructions to get the work done, and up and down, right? So that's a slow process, but it's okay because we don't do this very often. Okay, we do it at the beginning of our process. We create a bunch of threads, and maybe if you have a complicated program, once in a while you'll create a bunch of threads, have them do something, and then wait for them to die. Okay, so pthread create, pthread join, these kind of stuff for creation and termination of threads. Well, you have to make them into system calls. Okay, so potentially they're very slow, but performance-wise, it's not a big impact because you don't do this very often. Okay, what about pthread mutex lock? Okay, go back to warm-up number 2. Do you do pthread mutex lock a lot? Yes, right? So if every one of these things is a system call, well, then it's going to be really, really slow. Okay, so that's one of the problems with the one-to-one approach is performance. Okay, if you do a lot of these things, pthread mutex lock and unlock, if they all have to go down here, so you have mutex implemented in the kernel, okay, then it's going to be really slow. Okay, so all right, so that's the problem. Okay, if you think about your implementation, so think about warm-up 2 again. When you call pthread mutex lock, is the mutex locked? Most of the time the mutex is not locked, right? Most of the time, if you use a thread, they're all sleeping. None of them have the mutex locked. Okay, so therefore, a sort of an obvious optimization that you can do is that you can do the following, right? If you call pthread mutex lock, and the way I can implement it is such that if you find the mutex available, okay, it should return quickly and have the mutex locked. Okay, so again, go back to that picture, right? Here's user space, here's kernel space. Over here, you call pthread mutex lock. Okay, if the lock is available, do you have to go into the kernel? You don't have to go into the kernel at all, right? Okay, why do you need to go into the kernel? Right, because the threads are implementing the kernel. So if you want to lock something, it's only your thread that's locking it. You don't have to wait for another thread. Right? If the threads are implementing the kernel, that means that some of the queues that you use to wait for other threads, well, they're sitting in the kernel. Okay, so therefore, if you need to switch to another thread, well, then you have to go into the kernel. Right? Because at the user level, you don't know how to switch from one thread to another because threads are implementing the kernel. Okay, so if you decide to give the CPU to another thread, that's the only time you have to come into the kernel. So if the mutex is available, you can just lock it, okay, and then you don't have to go into the kernel. Okay, so therefore, this is going to be a very useful optimization, trick that you can use to increase the speed of this one-level implementation of threads. Okay, so over here it says, Windows do it, Linux sort of have something similar. So, some of the system, actually implement things using the one-level model. Okay, for our kernel assignment, right, every process has only one thread in it. Okay, so we are sort of, doing this one-level model. Okay, but every process has a kernel thread and then have a user thread. Okay, so we are doing one-level model in Unix. All right, so there's a variation of the one-level model called the variable weight processes. And, this way, what you can do is that you can implement, multi-threading using one thread per process. Okay, so how do you, so those two terms seems to be contradicting with each other, right? You want to have multi-threading inside the process, but every process can only have one thread. So how do you do that? Okay, so over here in this, so this trick is called variable weight processes. Okay, so the idea here is that if you have a thread that tries to create another thread, what you have to do is to create another process. Okay, so when you create another process, what you can do is that you can say, well, when I create the process, I don't really want to call fork, right? Because fork means copy the user, copy the address space, copy everything. Okay, so in this case, we're basically going to use the same concept as sort of the extended address space. When you fork, a user process, you share the extended address space. But why stop there? Why can't you share more? Okay, so in this case, what you can do is that you can implement a separate system call called clone. Okay, this one allows you to create a child process. Okay, but in the child process, you can say, I want to share stuff. Okay, so what are you allowed to share? I'm allowed to share the address space, which is virtual memory over here. I'm allowed to share the file system, which kind of by default, when you create a child process, you're sharing the extended address space. Okay, so you can also share a bunch of all the other stuff. Okay, if you share everything between your parent and child process, I mean, aren't they just threads in the same process? Right, if you truly share everything. Okay, so this is called variable way processes, is that when you clone yourself and you say share everything, you pretty much, you're implementing, a thread, but now you have this extra data structure called the process data structure, but then in the process, they basically share everything. All right, so Linux, went with this approach, okay, to implement variable way processes, and some people will call, threads, so thread will become a lightweight processes, okay, because they are, you can create many of these things. You have some data structure that you share. You have some data structure you have to create, but then everything else you share. So, creating a thread is pretty lightweight. All right, so this is, another way to go, and Linux does that. So Linux actually, when they first tried it, it wasn't very successful. But later on in 2.6, they sort of got their act together and, get it fixed. So now, these days we are, using, using this particular approach of variable way processes in Linux. Okay. So what happens in this case is that you're going to have every user process has a thread in them. Okay. But now you can put a bunch of these processes together and say all their threads belong to a thread group. Okay. And in fact, they belong to the same user process. Okay. And also, in order for them to implement mutex, right, they're basically going to do what I mentioned before, right? You try to lock the mutex. If the mutex is available, you don't really want to go into the kernel. Okay, so that implementation is going to call futex. The futex stands for fast mutex. Okay, and towards the end of section 5.0, we're going to actually look at the code that implemented futex. Okay, so for now, we're going to talk about other strategies, and then we're going to later look at these implementation. All right. All right, so that's one level model. Okay, one kernel threads per user thread. Okay, the second one is called the two-level model. So the two-level model, the user library plays a major role. Okay, so again, right here's user space, here's kernel space. Right, here's your user process, here's the thread. Okay, where is the thread implementation? Well, the thread implementation is done in pthread, in user library. Okay, so when you compile, when you link, just like our kernel, one more number 2 assignment, right? In the end, you say -l pthreads. Okay, so pthread again is a standard. Okay, they can implement in the kernel, implement in user space. When you do -l pthreads on Solaris, okay, they have this implementing using the two-level model. Okay, so their implementation of pthreads is actually, part of it is in user space, part of it in the kernel space. Okay, in the good old days, in the good old days when they are first experimenting with multi-threads, per process, this entire library, pthreads library, is implemented in user space. Okay, so how can an entire thread library implement in user space? Okay, so over here you got to sort of use your imagination a little bit and try to sort of imagine how could that be. Okay, so there's no, there's no kernel involvement. Okay, so how does it really done, right? So again, when you link with the, the pthread library, the entire code get copied into the text segment, right? So all the codes that you have is over here. Okay, and all the, and over here you're also gonna have the data segment. The data segment, some of the, global variable is gonna come from the pthreads library. Okay, and then later on, when you create thread control block and those kind of stuff, well, they're going to be created inside the address space of the user process. Okay, so implementing the pthreads library, completely in user space, well, that means that everything is out here. Okay, the code is going to be in the user process because when you link with the pthreads library, the code gets sucked into your executable, so they're running right here, and all the data structures are over here. Okay, so you can see that maybe it's possible when you call pthreads create, you're going to access, you're going to execute code over here. It's going to create some thread control block, maybe in the heap or something like that. Keep track of all these data structure on the data segment. Okay, so maybe all these kind of stuff can be done. All right. So we're going to look at, the implementation, or the, sort of the strategy for implementing these kind of stuff. So there are basically two different ways of doing this. One is, this is called the N by 1 model. Okay, for one user process. So this is one user process. There are multiple threads in the user's, in the user process, but we only support the one kernel thread. Okay, so why do you want to do this? Well, one of the reasons, for historical reason, this is actually the earliest multi-threading, model. Okay, people start with this. So in the good old days, as far as the kernel concerned, there's no threads, there's only processes. Okay, so in this case, as far as the kernel thinks, the kernel is support a single user process. All right, so that's sort of a very, sort of important notion, right? In the one-to-one model, while the kernel knows that there are multiple threads in user process because threads are implemented in the kernel. In this case, the threads are completely implementing user library. As far as the kernel concerned, what threads? There's no threads in user space. Okay, there's only processes. Okay, so when this guy needs to switch to the other thread called thread switch, does the kernel get involved? No, right? Does the kernel need to get involved? So, recall the thread switch code. I mean, it completely can be done in user space, right? Okay, what about mutex? Okay, if I want to lock a mutex, do I have to go into the kernel? No, I don't have to go into the kernel, right? I mean, you can have a data structure, have a queue, you have a mutex, have a queue, have, condition variable, have a queue. I mean, all these things can be done completely in user space. Okay, there's no reason to go into the kernel at all. Okay, so this looks like really a good way to go, right? So why didn't Linux, choose this particular approach? Right, so we're going to talk about that a little bit. Right, so the idea over here is that if you imagine this, it can actually, everything can be doable, if you do everything in the user space. Mutex can be done, threads can be done, because all the codes are in the code segment of the user process, right? None of those code has to live in the kernel. Okay, so in the good old days, this is actually done. Okay, and the reason it's not done because of, some major problem. Okay, so going with this particular approach, is the major advantage is that it's super fast. Okay, there's no system call at all. Okay, none of these thread-related API. The entire pthreads library can be implemented in user space. All right, I mean, of course, you have to, if you want to switch from one thread to another, because you don't want one thread to hog the CPU, well, then you have to implement timers, right? But we've seen how to implement timers, right? You can, use some set I timer or something like that. And when a timer interrupt goes off, you can set up a Unix signal handler. And in the signal handler, you can, make this, the thread switch from one thread to another. All right, so all these things can be done in user space. Okay, so what is the problem? Right, the major disadvantage is what if a thread makes a system call? Okay, so over here, right, in user space, you have many threads, the same process, right? One of them make a system call. Okay, so this one calls read, right? Okay, it went into the, it went into the operating system. The operating system say, oh, it's a read, it's a synchronous call. So I'm going to start a disk operation. I'm going to suspend what? I'm going to suspend this process. The operating system doesn't know there are threads, right? So the operating system is going to suspend the entire process. It's not going to give the CPU back to this process. So when you make a system call, all the threads stops. Okay, so that's a major performance problem, right? Any thread makes a CPU, make a system call, All the other threads get blocked because they don't get the CPU at all. All right, so that's the problem of the kernel not being aware that there are user threads. Because then, even if this kernel has, 50 processors, it's not going to give another processor to one of these threads. Okay, so this guy, as it turns out, has a major performance problem. How do you solve this performance problem, right? So, for example, what you can do is that, you can have a non-blocking read, right? The normal read is a blocking read, right? You call read, you get blocked in the operating system, and the operating system, when it's completely done, read will return, right? So that's called a synchronous system call or a blocking system call. Okay, you can actually change that blocking system call or implement a non-blocking version of that system call. And this one we're going to call it for now, real read. Okay, so this is a non-blocking version. What it will do is it will return to you whether it was successful or not. Okay, and if it was not successful, well, one of the reasons it was not successful is because, it might take a while. Okay, so in this case, if the return code is -1, that means that I'm not done reading. Okay, so therefore what I would do is I will return an error number that says E would block. Okay, so this is the regular, Unix, signal error number. It says E would block. That means that if I continue to go with the system call, then we'll end up blocking in the kernel. All right, so this means that the data is not there. Right, when you perform a read, is it possible your data is there already? Right, think about your, warm-up 1 and 2 when you make a read call. If you try to read a line, okay, and from a particular file, chances are the entire file is in memory already. So every time you call read, right, the first time you call read, you open the file, you call read. If the file is small, the entire file gets sucked in from the disk into memory. So it's sitting there waiting for you to read. So most of the time when you call read, it returns really fast because the data is there already. Okay, but when the system gets busy, then some of the things get swapped out and stuff like that. But otherwise, the data might be there already. Okay, so this guy can actually return with all the data, in hand, so you're ready to return. But in case you really need to perform a disk operation, what it will do is it will return with -1 and set error number to would block. Okay, so this means that the read is not successful. You have to find another way to read it. Okay, so in this case, what you can, in this example, what you can do is that you can go wait for a semaphore, and the semaphore is waiting for a semaphore for that file descriptor. Okay, so over here you try to read from a particular file descriptor right here, right? This is the same file descriptor. So every I/O devices, well, there's a semaphore that you can wait for. So when that I/O become completed, then the semaphore is going to get posted. So therefore, over here you sort of assume that there's going to be some kind of a producer-consumer data structure that you're using. Okay, so therefore, when this device is ready, you can read the next data from the from the shared buffer, and that will be the data that you're supposed to return from here. All right, so in that case, what you can do is that this one, the semaphore wait, again, is that user level or is that kernel level? Right? If the mutex and stuff like that are implemented in user space, well, so can the semaphores. Okay, so all these things are done in the semaphore, but then you have to set up a signal handler to say that when this I/O device is finished, associated with this file descriptor, okay, then that particular a signal handler is going to get invoked, and in that signal handler, you're going to call sem post. Where is that? Okay. So the opposite of sem wait, from the sort of the pthread slides, there's something called sem post, and that's the one that posts the result for waiting for the semaphore. All right, so it can be done that way. Okay, so this way, again, your thread will not be blocked. Okay, it was sitting in a user level queue, just like waiting for a mutex. Right? If you go wait for the semaphore, you are waiting in the semaphore queue. Okay, and the semaphore queue is very similar to a mutex queue. So they're all user level data structures. So the only time you're in the operating system is when you call real read. All right, so again, this way that you can, try to keep everything in user space. Unfortunately, this doesn't really work for every devices. Okay, that there are devices that, that this particular way of interaction doesn't really work. Okay, so this is really not a general solution. All right. The second way of doing these two-level approach is called the n by n model. Okay, so in this case, the kernel is aware that there are these user level threads. So the kernel allocate, several kernel threads to support that. Okay, so the user level thread is still quite many. So the idea over here is that if one of them makes system call, well, it's going to get blocked using this thread. All right, so this guy makes a system call into the kernel. We're going to allocate this kernel thread to support it. Right, so now other threads, are they allowed to run? Yeah, right, because the kernel is aware of user threads, and then if other threads they want to run, they can continue to run. Okay, if they make another system call, then another kernel thread is going to support it, another kernel thread support it. But pretty soon, you're down to the same picture as the n by 1 model again. Right? If all three of these threads are making a system call, and now you have 3 user thread left and 1 kernel thread left, if you make another system call, what happens? Same thing happened as before. Okay, so what is the solution for this? Well, the main difference between the n by n approach and the n by 1 approach is that the kernel is aware that the user has threads. All right, the other one, the kernel have no idea that they're a user thread. Okay, so now the kernel is actually can be a little more smart. When you use up the last thread, inside the kernel, can they create another kernel thread? Sure, why not? Okay, so the simple solution is that when you run out of thread, the kernel will just support and create another thread. All right, create another thread, create another stack. So it's not that, cheap because you have to do a lot of, you have to create a bunch of stuff. All right, but it can be done. Okay, the textbook talk about these other kind of deadlock, but the idea is, again, is when you use up the last thread, then the user process is blocked out. All right, so as it turns out that, this particular approach is to create a new thread in the kernel when you run out of threads, or when you use up the last thread, and that's the solution that Solaris takes. Okay, so when you're doing your warm-up number 2, you're running on Solaris, now you know that Solaris is running the n by n solution. Okay? All right, so there's another problem with a 2-level approach. Okay, that problem is called priority inversion. Okay, so one of the problems is the I/O, right? So Solaris certainly solved that problem, but every time you run out of threads, you create another one. Okay, so it is important that the kernel is aware of user threads, then you can do something like that. All right, so the old approach of the n by 1, basically nobody do that anymore. Okay, all right, so that's the I/O problem, but 2-level has another problem, it's called priority inversion. Okay, so remember I mentioned to you that you should resist all attempt to set priority in the user level thread. Okay, because once you have user level thread, then, it is possible for the low priority thread never gets to execute. Okay, so there are priorities in user level thread, so there are also priorities in kernel level threads. Okay, so the problem with priority inversion is that, let's say that you're using priority level. So user level, you have 3 threads. Okay, so this is the high priority, here's the medium priority, here's the low priority thread. Okay, inside the kernel, you also have, high priority, medium, and low. Okay, when this thread, make a system call going to the kernel, okay, do you have any control of which thread is going to pick it up? All right, so the idea over here is that, if you're using the 2-level model, then you don't really know what's going on in user space. You know that there are multiple threads, but you might not aware of their priority levels. Okay, so it is possible you will end up supporting this kernel thread with a low priority kernel thread, and then support this low priority user thread with a high priority kernel thread. Okay, so if both of them are running in the kernel, then this guy will actually has higher priority over this other one. It will block out this one. Okay, so what's the problem with that? Well, the user is going to get very upset, right? They say, hey, I went through all these trouble to saying that these things have a certain priority, and now inside the kernel, you switch it around, so this guy actually end up to have, higher priority. Okay, so it looks like pthreads library is not following its contract to say that this has higher priority over this one. Okay, so the priority is inverted. Okay, so that's the general problem of priority inversion. Okay, priority inversion problem has been studied to death in the operating system literature because, things get more complicated when you have more processors, when you talk about distributed computing, all kinds of stuff. So these are sort of popular, research problem. And it turns out it's a pretty difficult problem to fix. Okay, you try to plug one hole, talk about one scenario, say, oh, this is a way we can get around it. And then once you plug that hole, then another hole pops up. There's another place where you're going to end up with priority inversion. You plug that hole, there's another place, a priority inversion problem. Okay, so it turns out that that there's a completely different approach in these implementation strategy to try to avoid this problem. Okay, so this is kind of a serious problem. So we're going to briefly look at this other approach. Okay, this one is called the scheduler activation model. So it's another way to do two-level. But in this particular case, what we try to do is to try to decouple the kernel from user. Okay, so instead of the kernel trying to do thread scheduling for the user's thread, the kernel says, I don't really want to get involved. Okay, well, I want to let the user process decide how it wants to schedule the user thread. Okay, so in that case, can you have priority inversion? Okay, if you go to the previous picture, okay, these three threads, if the kernel don't want to schedule these threads, right? I mean, go into the scheduler, doing whatever, first come, first serve or whatever, you try to figure out which to run. It has no idea what the priority levels are at the user space, right? So therefore, it's going to make the wrong decision. Okay, if we leave that decision to this guy, okay, if this guy scheduled it incorrectly, well, then it's not the kernel's fault. Okay, so the idea over here is that in the pthreads library, you will also implement a user level scheduler that can schedule among these threads. You don't let the kernel decide. Okay, so in that case, what does the kernel do, right? Well, so the kernel job is that, again, the thread is a abstraction of the processor. So inside the kernel, the only thing the kernel will do is to offer processors to user-level processes, okay, and then let the processes decide how they want to schedule these threads. Okay, so the picture sort of look like this. You have here's a user process. Okay, inside the user process, there is a user scheduler that knows how to schedule user thread. Okay, and here the kernel's job is basically to assign CPU to processes. Okay, in this picture, the kernel scheduler has decided that these three processors are dedicated to this user process, and these other processors are dedicated to this user process. Okay, and this user scheduler over here, that guy has decision to make how they want to schedule its thread onto these three processors. Okay, so therefore the kernel doesn't really make that decision anymore how to schedule user threads. Okay, so let's see how this actually helps even in the previous scenario where you have I/O problems. Okay, so let's look at a little more detail by using using this example. All right, so this example, we have three processors and we have two user processes, and each user process has two threads running in them. Okay, so what happens is that when the the CPU become available, okay, the operating system is actually going to make an up call and try to offer the CPU to the user process. Okay, so it's kind of a sort of a different approach. In this case, what it will do is that one of the CPU become available. It's going to ask the user level scheduler A to say that, hey, do you have any use for this process, for this processor? Okay, this guy will either say I can use it or I cannot use it. Why would this guy say I cannot use it? Well, maybe all the threads are getting blocked, waiting for something, and then they can't really use the CPU. Okay, so if it has idle threads, if it has a thread that can execute, then most likely it will take the CPU, and then it will decide which thread to run on the CPU. Okay, so over here, this guy in this example, right? You offer this guy to the to the user scheduler, and it will choose which thread to run on the CPU. Okay, so in this example, it will choose one thread, right? It will choose A1 to be mapped to that particular CPU. So now this thread is running on the CPU. Okay, so what can happen at this point? Okay, then it will try to offer, another CPU become available. Again, it will offer either to, this user process or that user process. Well, that depends on the CPU scheduling policy. Okay, the CPU scheduling policy can say that, well, this guy already has one processor, so I'm going to offer to another processor. Or it will say that, well, this user process has been, idling too long, maybe I'll offer another processor. Well, depending on whatever the policy is. This example, it will offer the processor to user scheduler B, and the user scheduler B say, I'm going to run B1 onto this user processor. Thank you very much, operating system. Okay, so they will go from there. Okay, so now what happens when this thread make a system call? Okay, so this guy is using the processor, right? We know how system call works. It makes a system call, it transition into the operating system. So at this point, the CPU, so that the operating system took the CPU back. All right, so the CPU was offered to this guy before. Once this guy make the system call, now the CPU is taken back, and we start all over again. Now you have a free CPU, you can offer it to anybody. Okay, you can offer it to this guy, you can offer it to this guy, and the CPU's decision, or sorry, the operating system decision to decide who to offer the CPU to. All right, so again, the operating system scheduler work with the user level scheduler, and the user level scheduler decide which thread to run on. Okay, there's no priority inversion problem, and then there's also no problem with blocking inside the operating system. All right, because if the operating system wants, it can offer the CPU back to this thread. Sorry, back to this user process. Then you can run this thread. All right, so using this approach, you avoid the I/O problem. You can also avoid the priority inversion problem. Okay, if the CPU, the operating system decide to offer the CPU back to process number B, then B can run the second thread. Right, so now these things get running for a while, and then eventually the timer goes off, right, because you don't want them to hog the CPU. The timer goes off. What the timer goes off, that's this hard interrupt. You're trapped into the operating system. Okay, so at this point, the operating system can actually take a CPU away from one of these, from the user process. Okay, you can say, hey, you no longer have this, you no longer have the CPU anymore, right, because the CPU has been interrupted. Okay, so some interrupt can come to the CPU get interrupted, and this guy get taken away from the operating system. Right? Remember, as soon as you go into the operating system, the CPU is taken away, and now the operating system can decide to offer the CPU to any of the user process it wants. Okay, so this approach actually nice and clean. It solves many of the M by N problem. Okay, and it also is very convenient to implement all these operating system features. Okay, but if you look at all the popular system, Linux, Mac, Windows, or whatever, nobody's implementing this. The reason is because this is new research, and people are very, we sort of talk about we want to make the operating system interface as consistent as possible. So any kind of a new idea, people tend to, shy away from it. Right? So this is kind of a brand new idea. When the CPU become available, you're going to do an upcall to the user scheduler. So, you basically have to change the operating system to quite a big extent, or especially you have to change all the application program to be able to work with this particular concept. Okay, so even though this is a really nice idea, it's really not being used in a major operating system. All right, so that's all the strategies, and now we're going to look at how the threads are implemented. We're going to look at a lot of code. Some of the code are very tricky. So don't feel bad if you don't understand it the first time. It takes quite a few looks to eventually figure it out. Okay, very tricky code. Okay, so we're gonna see how so you sort of have an idea how to implement threads one-to-one, M-to-1 or whatever. So now we look at how the mutex are getting implemented. All right, so here's some of the terms. We're going to look at how spin locks and what they are, how blocking locks are implemented and what they are, and finally we're going to look at the implementation of mutex. Okay, so keep in mind that mutex can be implemented in the kernel and user space. Okay, so these things sort of have general applicability. Okay, the challenge in implementing mutex, right? So mutex is mutual exclusion. Okay, so you're mutually exclusion from what, right? So if you are this pink thread that's running over here, who do you have to worry about? Okay, so there are 4 things you have to worry about. Okay, number 1 is that you have to protect yourself from accessing shared data structure that are used in the interrupt handler. Right, so over here you are keeping mutual exclusion from the interrupt handler. Okay, so we sort of see how those things are done. Right, we're going to see a little more detail now. And number 2. You're going to make sure that another thread that are running in the same processor, they don't interfere with you. Okay, we talk about mutex, how do you lock and things like that, right? This guy the typical way of dealing with number 1 is to done through to interrupt masking. Okay, you mask the interrupt, right? And this guy you use mutex. Okay, what about 3 and 4, right? This thread that are running over here, do you have to worry about interrupt in another processor? Well, if this guy just happened to be updating the same data structure as you, well, then you have to worry about it. Okay, so therefore, you might have to worry about this, number 3. Number 4, you have another threads that are running in another processor, okay, and both of them are accessing the same data over here, well, then you have to worry about it. Right? So this thread and this thread, they might be the same user thread inside the same user process. So of course they might access the same, shared data structure, in the heap, in the, in the global, in the data segment, stuff like that. Okay? So you have 4 things you have to worry about. Okay? So when we use mutex, these mutex we have to worry about, well, do we have, multiprocessor? If we don't have multiprocessor, then 3 and 4 are gone. Okay, so we have an operating system that only works on a Unix processor, well, then maybe it's simpler. Okay, but if we know that there might be multiprocessor stuff, then we've got to make sure that your code also works in the multiprocessor case. All right, so we're going to look at these things. We're going to start with a simple solution, and we're going to get more and more complicated. Okay, so the first thing we're actually going to look at is number 2 over here. Okay, is that, you don't have interrupts, and you only have threads on the same processor, and you only have a single processor. What kind of implementation you need, and we sort of see that before, okay? And we're gonna see, we're gonna look at more details. All right, so this thing is called straight threads implementation. Okay, everything happened in thread context. That means no interrupts. Okay, we're gonna assume interrupt never happens. Okay, and how do you implement mutex in that case? Okay, no interrupt, so no preemption, right? So again, the idea of preemption is that you get a clock interrupt, right? One thread using up the CPU for too long, the clock interrupt happens to say, hey, I'm going to run another thread. Okay, if you have straight threads, that means that there's not even that. All right, so very simple. You only give up the processor voluntarily, and there's only a single processor. Okay, we don't have 3 and 4 interference from things happening in the Unix processor. We're going to use this picture to represent a thread. Okay, so a thread, right? A thread object or thread control block is right here. Okay, and the thread has a stack. Okay, so this picture is kind of misleading, right? Because these things don't really sit right next to each other. Okay, the thread control block, if the thread is implemented in the kernel, this one is in the kernel. This one might be the user thread stack, so it's in user space. And if you use the one-to-one implementation, while the kernel also have the thread control blocks in the kernel, and the kernel also has a kernel stack supporting a kernel thread. All right, so this picture is kind of misleading, but we're going to use this picture to represent a thread, knowing all these different ways of implementing it. Okay, so just need to sort of focus our attention on the fact that there's something called a thread control block, and this thread has a stack. Okay, and we've seen that there are things that sort of points into the stack as before, right? Okay, so I guess that's in a different picture. Okay, so we're going to sort of draw this picture. Say that every thread. Okay, so here is a thread, here's the threads all over the place. Okay, there is one thread that is currently running on the CPU, and we're going to use the global variable to point to it, and this one is going to call it the current thread. All right, so this could be all the thread in the same process, okay, or this could be all the thread in the kernel or whatever. This is a very general picture. Okay, so the idea over here is that every thread belongs to a queue somewhere, except for the one that are running in the CPU. Okay, the one that's running in the CPU doesn't belong to any any queue. Okay, it just have a global variable point to it. All right. So if this thread is completely implemented in user space, right, then all these threads belong to one user process. And where is the current thread? Well, it's in the data segment of the address space of the user process. All right. If this is the kernel, the kernel threads, then all these threads are running in the kernel, and the current thread is going to be a global data structure, a global pointer inside the kernel's data segment. All right, so work either way, right? Okay, so let's. So over here, there's also something called a run queue. I mentioned that before, or the ready queue. The run queue is a queue of threads that are waiting for the CPU, and they're not waiting for anything else. Right? So everybody over here is in a runnable state, and this guy is in a running state. Okay, And this guy is in a waiting state, right? It's waiting for mutex. And also there could be every I/O device. I/O number 1 has a queue, right? I/O number 2 has a queue. There are tons of queues there. Every thread can only be on one queue. Does it make sense for a thread to be in 2 queues? No, right? Okay, because again, a thread is a thread of control. You're executing code, right? Your thread gets suspended when it go wait for something, right? So it can only wait for one thing. It's the stuff that it just executed. The last thing, it either make an I/O call or it makes a mutex call or something like that. So it get queued onto one of these queues. Okay, and then when you get I/O completion interrupt, a queue, sort of a thread from I/O queue get appended into the run queue. When you get mutex unlock, and if this thread is going to be the next thread to use the mutex, then you get removed and then you get appended to the run queue. All right, and then the CPU scheduler take the first job, well maybe the first job, maybe the last job, we don't know. Take one of the thread from the run queue and then make it into the kernel thread, make it into the current thread. If this guy decides to give up the CPU. All right, so this is sort of the global picture. Sort of keep this picture in mind, that every thread has to be somewhere. Okay, if you have a thread that's floating around, then you have a bug in your kernel. Okay. All right. A little more detail, right? In the thread control block, or in the thread control block of the thread object, there's a context area, right? Inside the context area, there's a stack pointer. The stack pointer points to the top of the stack frame over here. Okay, even though the picture might be again misleading, right? Because this guy might be in the kernel, and this is the stack in the user space. But the idea over here is that, yeah, you need to keep track of it. So there might be several levels of indirection, but in the end, well, there's something over here that points to where the user stack is. All right? So that's the picture we're going to go by, the simplified picture. Otherwise, things get too messy. All right, and this is the picture for the thread that are suspended, right? Because if the thread is currently running the CPU, then the stack frame is going up and down, and this thing is outdated. Okay, so only when the thread gets suspended, this picture is correct. The stack pointer points to the top of the user stack, and the last stack frame is switch. Right? All right, so now we're going to look at a little more detail. Maybe a different version of switch. That's the next thing. All right, so we're going to have a slightly different version of switch. Okay, so this guy, we're going to call it thread switch. Okay, so thread switch is the one that eventually we're going to sort of, I guess in section 5.1, we're going to make it actually be able to work with interrupt. Okay, so this, right now we're going to see a very simple version that only work with, other threads, and there's no interrupt at all. Okay, so this is a simple version. We're going to continue to make it more and more complicated. All right, so over here, this is a thread switch, very simple as before, right? What we had before was that, we actually take the switch that we saw before has the next thread as one of the arguments. Okay, so this one is a little different because we're going to work with the previous picture. We're going to actually deal with the run queue. Okay, because when you try to switch to another thread, that means that you're going to take the first job off of the run queue and then have it run in the CPU. Okay, so therefore inside over here we're going to involve the run queue. Okay, so the thread that's calling thread switch is ready to give up the CPU, which means that that thread, right? So if it's ready to give up the CPU, so where is that thread? Okay, that's the thread that's currently running. It's ready to give up the CPU. So what does it have to do? Okay, it has to add its thread control block to one of the queues over here. Okay, it can add itself to a mutex queue. So maybe this, called thread switch is because it's in the implementation of pthread mutex lock. Okay, try to lock a mutex. The mutex is not available, so it has to get on the mutex queue, and then it will give up the CPU. Right? If it's making a system call, it's going to get on one of the I/O queue, and then it's ready to give up the CPU. All right, so this is straight thread. There's no interrupt. You're just switching to another thread. So you have to sort of give up the CPU voluntarily because there's no interrupt. All right, so we're going to assume that this guy has already appended itself to one of the queues. Now the current thread is pretty much, still pointing to it. Okay, but this thread is somewhere else already. Okay, so then it will call thread switch. So what is the code doing over here, right? It dequeued the next thread from the run queue. okay, and make current, make old current equal to current thread, right? So here's the current thread. It points to, this thread that's calling this function, okay? And here's the run queue, right? Run queue, okay? So we dequeue the first one over here, have next thread points to this guy, right? Next thread is equal to dequeue of run queue. This guy is off. Old current equals to current thread, right? Old current is this guy. This guy point to wherever the current thread is pointing, okay? And then current thread points to the next thread. The global variable current thread now points to this guy, right? Which has been removed from the queue, okay? And then what we do is we call swap context. All right, so the current thread is the thread data structure, right? Thread control block, okay? Inside over here, there's the context area, okay? And then this guy also has a context area. So what we do over here is that we're going to swap the context area in the sense that we're going to save the CPU's context into the old current. So where's old current? Old current is pointing to this guy. Okay, I have the pointer over here. Old current pointing to this guy, and the next thread is pointing to this guy. Okay, so the swap context operation will write out the CPU context into this guy, and then load from this the new thread's context into the CPU. All right, so remember what's in the context, right? The context is the saved context of that thread. Okay, so if you're going to give up the CPU, well, then I have to save my context. So I'm going to save my context in right here. Is this the right place to save it? Yes, right, because I said that this data, this thread control block belongs to the one that are coming in. Okay, so this guy who's calling, that's the thread control block. That was pointed to by the current thread. Okay, so the current thread is going to save its context into the thread control block. Okay, and then it's going to load the context from next thread's context. So next thread right now is pointing to this data structure, right? That one has the saved context over here, and that one is going to be restored into the processor. Okay, so remember what is the most important part of the context, right? It's the stack pointer. Okay, so over here you're gonna restore a bunch of the register from the context area, restore the stack pointer. So after you do this, you will be running in the other thread. Okay, because the current thread now is pointing to the other thread, and now after you do this, the stack pointer is going to point to the stack of the other thread, right? And then the last few instructions in the C function, right? Thread switch, last two instructions over here, or last 2, 3, is going to restore the base pointer, is going to restore the instruction pointer by returning to whoever that calls switch. Or in this case, whoever that calls thread switch. All right, so what we're seeing over here is that we have replaced switch with thread switch, and thread switch knows how to deal with the run queue. Okay, so that's the only difference between this one and the previous one, is that this one deals with the run queue, and also we use a slightly different function. It's called swap context, or swap the entire context that the processor that store everything onto this particular thread control block, and now you can restore them. Okay, so this context area has a lot of other stuff, all the other registers that are not explicitly saved onto the stack, well, they're also in this area. Okay, so as soon as you finish calling this one, and again, very similar to switch, one thread comes in and the other thread goes out. Okay, and every thread, when they need to give up the CPU, they all come here. So when this guy returns, it's going to return to this thread. When it was suspended, either it was waiting in the mutex queue, or it's either waiting for I/O because it called read and it trapped into the operating system. It's going to continue from exactly where it left off. All right, so this is our new switch function. Okay. All right, so given that this is the way to switch, how would you implement a mutex? Okay, so now again we are doing straight thread. There's no interrupt, and there's only a single processor. Okay. So to implement pthread mutex lock, right, we can simply do the following code. If the mutex is locked, then we go wait on the mutex queue, right? We enqueue this thread, we enqueue current thread onto the mutex queue, and then we call thread switch to give up the processor. Does that make sense? Right? If the mutex is not available, well, you can queue yourself on the mutex queue, and then you call thread switch, give up the CPU. Okay? Eventually, when thread switch return, when will thread switch return? Right, so remember this code puts you onto the mutex queue, You got to wait until somebody called pthread mutex unlock, and you're at the head of that queue, then you get moved back into the run queue, right? And when you get back into the run queue, you have to go all the way to the beginning of the run queue, and then when somebody else called thread switch, that's when you will return. Okay, so imagine that, when this guy return, what picture, what kind of stuff has to happen in order for this thread to run again. Okay, at this point, you switch to another thread. Okay, so this function, as far as the calling thread is concerned, doesn't really return until quite a bit later. Okay, if the mutex is not locked, mlock equals to 1. Is that okay? Do we have to worry about other threads competing with this guy? No, because we're doing straight thread, right? There's no other processor. There's no interrupt. Okay, so you cannot have something that interrupt between these two operations. Okay, so therefore you can just set the mutex lock equal to 1, and you own the mutex, and you return right away with the mutex lock, and you continue to execute. Right, so if the mutex is not locked, this function returns very quickly, and you continue to execute with the mutex lock in your hand. All right, what about unlock? Right, straight thread implementation of mutex unlock. If the queue is empty, so you are currently on the mutex, right? So you don't have to worry about anybody else because because we're doing straight thread. If the mutex queue is empty, then I just set the mutex lock to equal to 0. Now the mutex is unlocked. I return. I continue to do what I'm doing. The mutex will remain unlocked. Okay. What if the queue is not empty? Okay. If the queue is not empty, what I need to do is that I need to dequeue a job from a thread from the mutex queue, and then I'm going to enqueue that job in the run queue. Okay, over here it says I'm done. Okay, so this is kind of weird, right? Because at this point, if I call pthread mutex unlock, that means that I own the mutex, right? So therefore, mutex lock is going to be equal to 1. It's equal to true. Okay, now I'm going to return from here. Is the mutex locked? Yes, right, because it's 1, right? But do I own the mutex? No, right? Who owns the mutex? Well, the guy hasn't been running yet, right? I mean, there's this guy. This guy is the guy who's going to own the mutex. Okay, I just dequeue that from the mutex queue. I'm going to add it to the run queue, so that thread is not running yet. But that's the one that owns the mutex. Okay, is this okay? It's okay, right? Because if my thread kills my own other thread, is it my fault or is it the operating system's fault? I mean, it's not the implementation of mutex fault if you don't follow the protocol. Okay, if you have multiple threads that are trying to access shared data, once you unlock the mutex, you better not touch the guard, right? If you touch the guard, that's that's a death sentence. Okay, so over here, if you go back, you're gonna person who make mutex lock is gonna assume I don't own the mutex anymore. So I better not run any critical section code. I better not touch the guard. I better not modify any of those variables that I'm not supposed to do any of the things that I'm not supposed to do. And then you'll be okay. If you violate that protocol, then all bets are off. But in that case, your thread is killing your own threads. And that's allowed, right? The operating system is not going to prevent your own threads from killing your own threads. Okay? What if this is the kernel thread? Okay, if the kernel thread over here, once they unlock the mutex, it still go and modify the guard, or to go execute critical section code. Whose bug is that? It's the kernel's bug, right? Okay, if it's kernel code that's doing this kind of stuff, it's allowed to destroy other kernel threads. It's allowed to mess up other data structures. Okay, but then kernel is going to crash sooner or later. But that's allowed. Okay, so there's nothing that will prevent you from doing bad things. So therefore, it's very important to follow the protocol and do the right thing. All right, so this guy is going to return mutex lock equal to 1, but this guy doesn't own the mutex, and that's okay. All right, the next, eventually, when this other thread gets to run, it will return from where? It will return from thread switch. Right? This other thread you just remove into run queue. Okay? When that thing executes the next time, it will execute right here. All right? So, or to be more precise, right? When that guy, when it returns, it's gonna, because some other thread is gonna call contact switch. Okay, and then when it pop, EVP and stuff like that, and execute a return machine instruction, that's when this other thread is going to execute, and that thread is going to execute, right here. All right, again, tricky code. Take a bit to really understand this code and convince yourself that this code actually work in a straight thread situation. All right, is this code atomic? Yes, because straight thread, right? There's nothing to interrupt you. There's no other processor, so it actually turns out to be atomic. All right, so then we're going to see multiprocessor. Okay, things going to get a little more complicated. So one thing that you can do with multiprocessor, is that thread switch is no longer sufficient. Well, for a simple reason, inside thread switch, there is a global variable called current thread. If you have multiprocessor, if you have two processors, how many current threads do you have? Well, you have two, right? If you have four processors, you have four current threads. So current thread become an array. Okay, so therefore, the implementation, of course, what we had before is not going to work. Okay, so one way sort of people sort of deal with that is to assign a particular, sort of processor. You can number them, and every processor has something called an idle thread. Okay, so here's the code. What is the basic code for the idle thread? I mean, it's not complete. Okay. Oh, by the way, I didn't mention that. This code is actually incomplete because it doesn't really take care of this case. What if the run queue is empty? Okay, it doesn't really check if the run queue is empty, right? If the run queue is empty, what do you do, right? Everybody can, anyways, so incomplete. All right, over here, we also show an incomplete code for idle thread, right? Idle thread says, while one thread switch. Okay, of course, it doesn't really work, right, because you have to queue yourself onto a queue. So in this case, there's some missing code. The idea here is that you need to enqueue yourself onto the run queue and then call thread switch. Okay, so why is this the idle thread? I mean, it doesn't really do anything useful, right? So this, if you do things this way, when you go onto the thread switch, right, different version of a thread switch, can the run queue ever be empty? No, because there's always this guy, right? So for every processor, okay, you're going to have separate run queue, and every run queue, you will have at least one idle thread. Okay, so what's wrong with this approach? I mean, it's very, CPU intensive. If you implement your warm-up 2, right, warm-up 2, all the threads are sleeping, right? Now you have an idle thread eating up CPU clock. Okay, so maybe that's really not, I mean, these days with the day of, green computing, you really want to, shut down the processor and save energy. Okay, so this is really, it's a wasteful way to go. Okay, but it makes, things easier. All right, so now we look at, how to implement mutex when there are multiple processors. When there are multiple processors, right, the difficulty lies in this code, right? If mutex not locked, set mutex lock equal to 1. Okay, if you have two processors, both of them are doing exactly the same thing, right? And both of them just happen to belong to the same process, okay, or both of them are kernel, threads or something like that. Then this is the shared location, right? Mutex lock is this location right here. Okay, so it is possible for both threads to be executing, both CPU to be executing this instruction at the same time. Both of them thinks that the mutex is not locked, and both of them will simultaneously set it to 1. Right? I mean, of course, the bus is going to control who get in there first, but, it is possible this guy will read, followed by this guy will read, and then this guy will set it to 1, and this guy will set it to 1. Okay? I mean, there's no conflict in the sense that, you don't access the bus simultaneously, so nothing's going to explode. Okay? But the problem is that both threads think that they own the mutex. Right? So that's a no-no. Okay? So whatever the code that they're going to do afterwards is going to be invalid. Okay, so the previous implementation is really, not a very good one for multiprocessors. Okay, so how do we make sure that, that this doesn't happen? Okay, so one thing that we're going to do, let me get rid of this. All right, maybe we'll look at the next picture. We're going to use hardware to help us. So hardware is going to implement something called compare and swap machine instruction. Okay, so we're going to look at some high-level code for implementing this one, knowing that this one will be done inside hardware. Okay, so the idea over here is that you're going to implement this in an atomic operation. Okay, so this is called compare and swap. What you do is that you look at this memory location, okay, pointed to by the pointer address. Okay, that tells you which memory address to look at. And in the previous picture, that will be, this memory location for the mutex lock. Okay, and what you would do is that you will read that instruction, you read that location, compare with the old, and if, compare with the old, if it's equal to the old, then you set this memory location with a new value. Okay, so this is called compare and swap. If it's equal to old, set it to new. If it turns out not to be equal to old, then you don't do anything. Okay, so look at the code, right? If star pointer is equal to old, you read it, right? So here's CPU. Okay, CPU. Okay, and here is that lock thing in memory, right? Okay, you read it. Okay, you compare it against old. So old, the usual usage is that this is equal to 0 and this is equal to 1. You compare against the old. If it's equal to 0, then you star pointer equal to new, you set this guy to 1. All right, so if this guy is equal to 0, you set it to 1. Okay, and then you return, star pointer, the old value. Okay, so you know what the old value is. Okay, so in this case, when you return, if you return 0, so what does that mean? That means that you have changed it to 1. Right? Because if this one returns 0, that means that 0 is equal to old. Okay, 0 is equal to 0, so therefore star pointer is going to be equal to 1. All right, so if you call cast lock 01, when it returns 0, that means that now you own the lock, because now you know that memory location is set to 1. Okay, if this guy is already 1, right, then star pointer is going to be not equal to old. Okay, 1 is not equal to 0, so you don't set it to new, you just return. In this case, you return 1. So when this guy returns 1, then you know you didn't get the lock. Okay, so why is this atomic? Okay, so the trick is the following. This is the bus, okay, and a while back, I showed you pictures that there's one of the signals over here called the lock signal. Okay, we're going to use the lock to make sure that another processor cannot interfere with this operation. Okay, so we're going to expand the expand the bus to look at some of the important signal on the bus. Okay, one is called read, and the other one is called write, and then the other one is called lock. Okay, and then there's the address. Okay, and then there's data. Okay, so what happens is that when we read the old location, okay, so on the bus, we're actually going to generate a signal called read. So this one will read the data. Okay, so 0 meaning that we're not reading, 1 means that we're reading. Okay, and then what we're going to do, we're going to assert the signal called lock. Okay, so this signal lock goes on the bus. What it will do is it will lock out everybody on the bus. Okay, if you have 5 processors on the bus, if they see the lock, okay, they all get blocked out. Okay, so therefore I can do multiple operations with this memory without interference from any other devices or CPUs on the bus. Okay, so what I can do is that I can issue a read, right? So I would generate an address for the read. Okay, so this is the lock address. Okay, and I will read, at this point, I'm going to read some data from, from the bus or from the memory. Okay, so this one will go into the CPU, right? This data, 0 or 1, is going to go inside the CPU across the bus. Okay, and inside the CPU, I'm going to execute this instruction, try to compare them. If they're equal, what I'm going to do is I'm going to generate a write signal, write. Okay, I'm going to use the same address as the lock address right here. All right, and this time what I'm going to do, I'm going to write a 1 into it. Okay, so these two things going on the bus, one read followed by a write, okay, they are enclosed by the lock signal right here. So between this read and write, nobody else can get on the bus. Okay, not even, the internet, the network controller, even though, tons of packets might be flying across the internet onto your machine, they all want to interrupt the bus to transfer data from, the network controller, network interface card into your main memory. Do they get to use the bus? No. Okay, even though they are very, very high priority, this could be a user level threat, the lowest level priority thing on your machine, but you have a way to lock everybody out using this lock signal. Okay, so when I call this cast function, Okay, this cast function will have a hardware implementation where the lock will be asserted during these two cycles on the bus. All right, so this way I can make sure that this operation is atomic, okay, as far as the memory is concerned, because nobody else will be able to access the memory at that time. All right, this is how I guarantee, atomic operation. Okay, so basically this is the instruction to implement atomic operation, and then everything else can be built based on this particular machine instruction. All right, so we're going to see how this is being used to implement lock. Okay, so if it turns out that over here when you try to read from the lock is already a 1, then the second cycle on the bus doesn't exist. You will bring down the lock as soon as you decide that this function is going to return. All right, so the lock signal is actually a very nasty signal on the bus. It blocks out the entire system. Okay, if your system has 1,000 CPU accessing on this bus, none of them get to access memory at that time. Okay, so even though this is a really, really useful thing to implement a lock, you need to understand that this is very, very expensive. Okay, in terms of system resources, because during this time, when the lock signal is asserted, the bus only belongs to one processor and nobody can share it. All right? Okay, so you can use lock to implement something called spin lock, okay, or busy lock, busy wait or something like that, right? Over here, I say while, okay, so here's another way to implement mutex. I say spin lock using mutex. Mutex is just a variable for that lock, okay? So I say cast mutex 01. Right, so this one is going to call cast, and when it returns 1, that means that it doesn't have the lock. So I'm going to call while and stay in this loop forever. It's an infinite loop, keep staying over here. As long as it returns 1, I will stay here, do nothing. Okay, and then if it returns 0, then I'm going to jump out of the while loop and return, and I own the lock. Okay, so this is called spin lock. It spins the CPU, waiting, looking for that lock to become 0, so they can set it to 1. While block out the entire bus, right? So over here, if you look at the bus, right, here's the lock signal on the bus, okay? It's going to go from 1, and then it's going to go 1, it's going to go, okay? So only a small amount of time, other devices are allowed to use the bus, while this guy is locking out the bus most of the time. Okay, so clearly this is not a good implementation, okay? But it works, okay? Not very efficient. Okay, and spin unlock, you own the mutex already, right? So you unlock the mutex and setting it to 0. All right? A better spin lock to avoid this situation. Okay, so why is this bad, right? If you already know that the lock, somebody owns it, okay, if somebody owns it, then why do this? Okay, you're just blocking everybody else out on the bus. Okay, so over here, here's a better spin lock. While it's true, right, you still have an infinite loop. If the mutex is equal to 0, you go try to read it. Okay, if you read it and if you see that it's available, you try to grab it using cast. Okay, if you already know that memory location is 0, you try to change it into a 1 in the next cast, operation to change it from 0 to 1 using, what we saw before. Okay, so it is possible that at this point you see it's beginning at 0, but when you execute this instruction, in the meantime, somebody else grab it. Oh, bad luck. Okay, then you go back and do this again. Okay, so if you do that, what happens is that you're going to do this a lot. Okay, so what's going to be going on the bus, right? You're going to generate recycle. Okay, you're going to generate recycle. Okay, you're going to read like this, right? But there's no lock. Okay, eventually when you see the mutex go to 0, then you will do the lock, right? And then you try to do a read and maybe a write. All right, so this way, most of the time, yeah, you are still using the bus, but you're using the bus only a small amount of time, right? This picture is much more efficient than this picture. Okay, so that's why this is a better implementation of the spin lock. Even though at the moment the lock becomes available, you might not get it right away, then you have to go there and wait some more. Okay, but at least you're being friendly to the rest of the system. All right? Okay, so spin lock is very wasteful, even though it works. Okay, so if you want to do pthread mutex lock, you can use spin lock. Okay, but then if you know that somebody else has had the lock and has to use it for a very, very long time, then you're wasting CPU cycles, right? Because this thread that's doing this, why is it wasting time doing this? Okay, it needs to get on the mutex queue and wait for it. All right, so basically we'll go back to the previous implementation and say, well, that's actually a better way to implement, except that we have a problem, right? It doesn't really quite work. Okay, so we need to get it to work. Okay, so eventually, yeah, we sort of need to, if you want the lock, you should get on the queue and wait for it. Okay, so it sort of go back to the previous approach again. Okay, for multiprocessor, then bad things might happen, right? So over here we're gonna see this is called blocking lock. Okay, so you're gonna check the mutex, see who holds it. Okay, if the mutex holder is not equal to 0, that means that somebody owned the mutex. Then you will go wait. You can queue the current thread, right? So this means the current thread for this processor. You go wait for that in that queue. Okay, and then you give up the processor. Oh, camera operator, can you fix this one? That one is working. Okay, or you can turn on the projector screen in the back. All right, maybe some people can move for now. All right. Okay. Is the camera operator in the back?
Sorry, Professor. The volume of the trump's a little low. Can you say that again?
Yeah, this screen is out. All right. Okay, so let's continue. All right. So if the mutex. All right. Thanks. Okay. If nobody's holding the mutex, then the current thread becomes the mutex holder. All right? If you want to unlock it, you want to see if anybody's waiting for it. So this is, again, very similar to the previous case. You want to see if anybody's waiting for it. If the queue is empty, nobody's waiting for it, then you turn the mutex holder equal to 0. If somebody's waiting for it, you dequeue them, and then you can queue that into the run queue. All right? Similar as before. Okay? But, again, this only works on a uniprocessor, because you're going to have problem accessing the shared variable, right? Okay, so this code doesn't work for the same reason as before. Both processor 1 and 2 can be executing threads that are executing this instruction simultaneously, so you're going to end up with a problem. Okay, so we need to fix this. Here is another example, okay, where there might be a race condition. Okay, so in this case, on processor 1, thread 1 is executing this code, checking the mutex holder is equal to 0 or not, and it sees that the mutex holder, let's see, thread 2 holds the mutex, right? So this mutex holder is not equal to 0, so thread 1 is going to enqueue itself onto the mutex queue. Okay? Thread 2 will be executing right here. It's ready to give up the lock. Okay, so what happens is that, thread 2 is giving it up, while thread 1 didn't really see it giving up the mutex. Okay, so thread 2 over here, right at this time, what it will do is it will check if the waiting queue is empty or not. Turns out it's not empty, so therefore, it's going to set the mutex holder equal to 0. Okay, so now, who's going to wake up this thread? I mean, if nobody comes here again, then nobody's going to wake up this thread. So it's kind of like a deadlock situation. Okay, so this example is, again, it's an example of a race condition. Due to this specific timing, you're going to create this, this problem. So the solution, right? Well, we saw a spin lock. Why don't we use this spin lock? Because now you have, things going on different processor, right? Okay. So the problem with spin lock is that it's really easy to figure out where to use spin lock, but it's actually not so easy to figure out when to use spin unlock. Okay. So spin lock, right? So what you will do is, right, is that you will put around this function, right? When you get in, you will lock, you'll lock the spin lock, and then in the end you will unlock the spin lock. Well, that should work. And also, when you try to unlock something, you spin lock it, and then you spin unlock it. Okay, so basically you use a smaller granularity mutex around something to implement a larger mutex. Okay, so the idea sort of works, except, something funny is going on here. All right, so you will put spin lock right here. Okay, there are two paths, right? If you put spin unlock over here, well, that's the same thing as putting spin unlock over here and spin unlock over here. Okay, so what's wrong with putting spin unlock outside over here? Okay, is that because you have a thread switch right here? Okay, so what happens when you call thread switch? Right, you give up the processor. Who owns the spin lock at this point? Right, the calling thread, somebody who's giving up the CPU, come to call blocking lock, right? Lock the spin lock. Okay, so over here we have two variables. One is one is the mutex holder, right? And the other one, the mutex, there's another thing called the spin lock. Okay, so over here, you lock the spin lock, and then you switch out to another process. Okay, can another thread, switch out to another thread. Can another thread ever get the spin lock? No, right, because you give up the CPU, right? So this thread owns the spin lock, so nobody else gets on. Okay, so you cannot put spin on lock over here, right? So that means that if you put spin on lock here or spin on lock here, that doesn't work. So where can you put the spin on lock? Well, there's only one place you put it, right here, right before it, right? Right before you call thread switch. Because right before you switch, you say, well, I'm going to give up the CPU, so therefore I should unlock it before I give up the CPU. Okay? But that doesn't work because between the time you unlock the CPU and you call thread switch, well, lots of stuff can happen. Okay? You're running on multiple processors, so, weird stuff can happen. So what kind of weird stuff can happen? Okay, so over here you have one thread that's that's running over here, right? It gives up the CPU. Okay, so it's waiting in the in this wait queue. Okay, and then they call thread switch, right? It released the spin lock already, so anybody else can get the spin lock. Okay, so let's say that as soon as it does this, the second thread comes in right away, and it calls blocking unlock. It locks the spin lock. Right now it becomes available, and it starts executing code. It will see that the queue, is the wait queue empty? No, right? Because this guy is on it. Okay, so this guy is actually going to dequeue thread 1 from the wait queue and then, make it runnable. All right, so it is possible if some weird timing happens that, when this guy starts, thread 1 will actually run on a different processor at the same time. Okay, so this could be running on a different processor, right? That's why we use spin lock because we have multiple processor. So thread 1 will run in the second CPU. At the same time, thread 1 is still running the first CPU. Is that a good idea? Okay, I mean, the problem with thread 1 running on both CPU is that now you want to switch out the context. What is thread 1's context? It becomes ambiguous, right? Because now you have two things running. Okay, they try to save state, and then, really weird stuff can happen. Okay, so basically you get into this no-no situation that thread 1 is running on two different processors. You should never have that happen. Okay, so this code doesn't work. Okay, so what is the fix, right? So the problem is that no matter where you put spin on lock, it's just not going to work. Okay, if you put it, after thread switch, then nobody gets the lock. If you put it before thread switch, you can say, well, I want to put it right here. No matter where you put it, something bad can happen. Okay, so the key to solve this problem, all right, the solution is to put spin on lock inside thread switch. Okay, so now we're going to have a thread switch that's, so how do you put spin on lock inside thread switch? Okay, so basically we have to pass this variable inside thread switch. Okay, that's no good, right? Because thread switch is just a simple function say I want to switch to the next thread. What is this, mutex spin lock doing over there, just for this purpose? Okay, so it's a little weird. So we're actually not going to show you the solution right now. Okay, we're going to show you the solution later on with the interrupt to see how this problem is being avoided. All right, so be aware that there's this weird stuff going on over here that if you implement spin on lock inside thread switch, that's really not an available option. So basically, we're going to scratch this entire code. Okay, so we're going to see how it's done in section 5.1 of the textbook. All right, so let's see how Linux solved this problem, right? We said that Linux, since the Linux kernel version 2.6, they use something called futex. Okay, so this one actually is another way for you to wait for some kind of a mutex, and this code we're actually going to see that this one actually works. So it takes a completely different approach, not like the sort of the blocking lock. Okay, so and the futex, basically the idea we talked about, right? In Linux, they implement the one by one approach. Okay, so every user thread is supported by the kernel thread. Okay, and the thread implementation is inside the kernel. Okay, so therefore, The problem is that when you access a mutex, you want to make sure that if the mutex is available, you want to grab it right away without going into the kernel. All right, so we're going to sort of use this. So how do you grab the mutex in user space when there are multiple processors? Okay, so that's the solution we're going to use is to use mutex. Okay, when the mutex is not available, okay, then you have to trap into the kernel. So therefore, you have to make a system call. We're going to use two system call to support this. Okay, so somebody else owns the mutex, okay, and you want to go into the kernel, you have to either make a call to mutex wait to wait for a particular mutex, okay, or if you're giving up, the mutex and the queue is the mutex queue is not empty. I'm going to use the word mutex and mutex interchangeably because they're the same thing here. Okay, the mutex queue is not empty, and then you're gonna give the mutex to the thread at the head of the mutex queue. Okay, so in that case, you have to wake up that thread. Again, that thread is sleeping inside the kernel, so you have to make a system call to wake up that thread. All right, so that system call is going to be called mutex wake in this example. All right, so now we're going to see how this is implemented. Okay, we're going to skip the attempt one and go straight to the actual solution. This is actually working code. I just want to make one notice is that textbook is wrong. Okay, this code is actually working over here. Okay, so the mutex has three values. Instead of a 0 and 1, it actually has 0, 1, and 2. Okay, so 0 means that the mutex is unlocked. 1 means that the mutex is locked, but nobody is waiting for the mutex. 2 means that it's locked, so 1 and 2 both means locked. 2 means that the mutex is locked with the possibility of waiting thread. Okay, so we don't really know if there's thread waiting, so therefore we don't really know for sure. We better get into the kernel and have the kernel figure out, because only the kernel would know for sure, right? The threads are implemented in the kernel, so if you want anything to be done correctly, well, you have to go into the kernel. Okay, so we're going to use the mutex value of 2 to indicate that particular condition. All right, so what is the lock? How do you do a mutex lock over here? Okay, so lock is going to pass in the mutex. Okay, you can see that we're going to actually use cast to implement mutex. Okay, so we know that this is to avoid multiple processors trying to step on each other's toes. Okay, so this one is actually very complicated, right? There's 1 cast, 2 casts, 3 casts called to implement mutex lock. Okay, so I'm going to briefly go over it. Again, this is very tricky code. You have to look at it several times to convince yourself this code actually works. Okay, so first I try to grab the mutex, right? I'm going to call the usual way 0 and 1. Okay, if it go from 0 to 1, this one will return 0. That means that I have the mutex. Okay, if this one returns 0, then it's not equal, so it's not going to go into any of these loop. This loop, you go in there only if you didn't grab the mutex. Okay, so if the mutex is available, this will return 0, and then you're out. Okay, so it does satisfy the requirement that if the mutex is available, then it locks it and then leaves. Okay, no kernel is getting involved. Okay, so if it's available, poof, poof, it's out. Okay, if the mutex is not available, then it's going to go into this loop, right? This is an infinite loop. If c equals to 2. Okay, so when this guy returns, it's going to be assigned a variable c, right? So if it comes here, then c is equal to 1 or 2, right? Because it only has 3 different values. If it's not equal to 0, it's equal to 1 and 2. If it's equal to 2, then what do? You go into the operating system, you wait for it. All right, you make the system call. You call the expensive step. Okay. Otherwise, if c is equal to 1, then you try, over here, you try to see if there's waiting thread again by saying that I'm going to be the thread that will wait for it. Okay, so I'm going to set it from 1 to 2. Okay, if I'm the one that's setting from 1 to 2, okay, then this guy will return 1, then I'm going to the kernel and wait for it. Okay, what if when I try to set it from 1 to 2, it returns something that's not equal to 1? Okay, then it could be returning 0. Right? Somebody might just release the mutex right between this operation and this operation. Okay, so therefore I'm going to go try again. All right, so over here it says, well, maybe I don't need to go into the operating system. I'm going to try again. So I'm going to try by doing the cast over here again. Okay, so over here I set it from 0 to 2, and again I'm going to see the C values. And then, if it turns out I don't get it, right, if this one returns 0, that means that I get it. If I get it, then I will return. Okay? If I don't get it, I'm going to go back into the inside of the do loop again and then try the previous step again. All right, so this is, so you need to convince yourself this guy works no matter what the timing is on the other processor. Okay, they will be executing the same code to try to lock the same few texts. And no matter what timing it is, wherever all the pointers are, this code will always work. Okay, also this code work with unlock, right? When you try to unlock the few texts, you try to see if there's somebody waiting or not. If there's somebody waiting, you actually have to go wake up that particular thread, make a system call. Okay, otherwise, you just set the few texts equal to 0, and then you're done. All right, thank you. Okay, so, again, tricky code. You got to take a look at it. Finally, there is, okay, so over here it just summarizes. Okay, we have different tools for different kind of locks, right? We have spin locks, okay, that you can use, but you have to use it in a very careful way so that it doesn't lock out the entire system. Okay, locking out the entire system is really, really bad because you're going to have these high priority interrupt. The high priority interrupt, like the networking interrupt and the disk interrupt, they want to transfer a lot of data over the memory bus. If you hog the memory bus, then those things is going to perform really poorly. Okay, and when your networking perform really poorly, and when your disk system perform really poorly, your user is going to be very unhappy. Okay, so therefore, use it as little as possible, but they are a very useful tool, and we already see how it can be used inside few texts. Okay, sleeping lock is good, but they're going to have this major problem when you have multiple processors. Okay, few text is an optimized version of the blocking lock, and we saw its implementation. All right, so your kernel number 1 assignment, you need to implement kernel threads. Okay, they are different from user threads. Okay, so kernel 1 and 2, you're completely inside the kernel. So all the threads that you're dealing with are kernel threads. And we have a non-preemptive kernel, right? Keep in mind, the Unix kernel is non-preemptive. Okay, and in the beginning of the next lecture, we're going to talk about the beginning part of 5.1, is what I was trying to get to. We're going to see how to implement thread switch and also the mutex lock, how they all come together. Okay, so keep in mind that the Unix kernel is non-preemptive. Okay, and the kernel is all powerful. Therefore, if you have any kind of bugs, it's your implementation that has the bug. Okay, so the kernel has to be bug-free. It should never deadlock. Okay, so when you try to use the mutex, you got to use it very, very carefully. And non-preemptive, which means great. There's not going to be competing thing from another thread. So it's almost like straight thread implementation, except you have to worry about interrupts. Okay, but we saw the interrupt code. How do you mask interrupt? And turns out masking interrupt is not that straightforward. Okay, so in the beginning of the next lecture, we're going to see how thread switching is actually work in the presence of interrupt. All right, kernel 3, you're going to implement actual user level thread. But at that point, I guess kernel 3, in the user space, every user process only has a single thread. Okay, so we don't really have to worry about multi-threading. All right, and again, Unix, the entire project are running on a single processor. Okay, so pretty much the only thing you have to worry about is interrupt. All right, so hopefully in the next lecture, in the first 15 minutes, I will give you all the code that you need, for kernel 1. Okay, so some of the code that you already see over here, they can be useful. Okay, over here. I mean, not the few text code, but some of the stuff you already can be used to implement mutex inside the kernel. All right, I'm going to stop here and see you on Wednesday to finish what you need.
This has been CS402 on Monday, June 23rd, 2014.